Now in linear algebra, we'll be looking at types of a matrix like symmetric matrix, skew symmetric matrix, Hermitian matrix and Skew-Hermitian matrix, orthogonal matrix and unitary matrix. And we'll be solving few problems on it. Please look at the previous slide, transpose of a matrix, for better understanding. Please like, share and subscribe this particular channel. Let us start now. Now coming to symmetric and skew symmetric matrix. Okay, important points. We'll understand each one: symmetric matrix, skew symmetric matrix, and in the case of complex numbers, how to go on within a matrix, so on. Okay. The first one, symmetric matrix. When A is equal to A transpose, then it is called as an A symmetric matrix. If you consider example like when A is equal to a matrix like 1, 2, 2, 4. Okay. When you find the transpose of it, A transpose, which is equal to nothing but get as 1, 2, 2, 4, 1, which is equal to nothing but A. So A is equal to A transpose. So it is known as a symmetric matrix. Come to the second one. Hermitian matrix. When A is equal to A conjugate transpose. What is a conjugate transpose? Is nothing but when in a matrix you have a complex numbers. Okay. I'm giving one example for you. If you consider A is equal to some matrix like 0, 2 minus A, 2 plus A, and 0. Now you have to find the conjugate transpose. Is equal to nothing but we'll find the conjugate of it and then whole transpose. First we'll do the conjugate of it, which is equal to nothing but we're changing the signs of a complex numbers, right? So it becomes 0, 2 plus J, 2 minus J, and 0. Now when you do the transpose of it, then it becomes nothing but A conjugate transpose, which is equal to 0, 2 plus J, 2 minus J, and 0, right? Which is equal to nothing but A only. In this particular case, it is known as an Hermitian matrix. Okay. Come here, third one. Skew symmetric matrix when A is equal to minus A transpose. Okay. For this also, we'll be giving an example like A is equal to 0, minus 2, 2, 0. Just find the transpose of it, A transpose. Then it is equal to nothing but it gets as 0, minus 2, 2, 0, which is equal to nothing but minus A. Yes or no? We got A transpose is equal to minus A. Then we can say A is equal to minus A transpose. Yes or no? So it is known as a skew symmetric matrix. Come to the next one. Skew-Hermitian matrix is nothing but when A is equal to minus of A conjugate transpose. Okay. I will be giving one more example for this one. Okay, if we consider a matrix A is equal to a matrix like 0, J, J, 0. Okay. Now we have to find the conjugate transpose of it. Then we get A conjugate transpose is equal to nothing but we're doing the sign changes of any imaginary numbers and we're doing the transpose. So it becomes 0, minus J, 0, which is equal to nothing minus A. Right? So we can say that A is equal to nothing minus A conjugate transpose. Yes or no? So it is known as a skew-Hermitian matrix. Come to the next one. Skew symmetric matrix has some points. Okay, important points you have to remember. The first one is nothing but the principal diagonal elements are zeros. In the case of a skew symmetric matrix, it is very important. Okay, come to the next one. The even order. Okay, for even order matrix in 2 cross 2 matrix, okay, the determinant is perfect square. Okay, always remember this one. Okay, in a skew symmetric matrix, even order matrix as a determinant is in a perfect square. If we consider an example for this one, okay, we know that when a matrix A is equal to something like 0, minus 2, 2, 0, find the determinant of it, then we get as 2 square. Yes or no? So for every even order matrix, we get an determinant as a perfect square. Come to the next one. For the odd order matrix, like 3 cross 3 matrix, the determinant is 0. Okay. If you consider an example for this one also. Okay. If you consider matrix A is equal to nothing but 3 cross 3 matrix. So it becomes 0, 1, minus 2, minus 1, 0, 3, 2, minus 3, 0. Is an skew symmetric matrix. Diagonals are 0, and you'll be looking at the determinant of this one. Then determinant of a matrix is equal to nothing but a 0, right, first term. Then minus 1 into, it becomes minus 6. Then minus 2 into, it becomes 3. So this becomes plus 6, and this is minus 6. So which is equal to 0. So these are the important things in the case of an skew symmetric matrix. Odd order determinant is always 0. Even order matrix determinant is always perfect square, and diagonal elements are zeros. Okay, coming to the next one. Orthogonal matrix is nothing but A into A transpose is equal to I. I is nothing but identity matrix, right? Like 2 cross 2 matrix, we write it as 1 0 0 1. Right, only diagonal elements will be there, which are always 1, and other elements are zeros. Now coming to the next one. Now in the case of a complex numbers, okay, unitary matrix is into A conjugate transpose is equal to I. I is again nothing but an identity matrix. Okay, now coming to the next one. Now the determinant of an orthogonal matrix is plus or minus 1. Okay, this is very important. When it is known as an orthogonal matrix, when A into A transpose is equal to I. Okay, in this particular case, we get the determinant as a plus or minus 1. Come to the next one. Now every square matrix A, okay, every square matrix A can be expressed in symmetric and skew symmetric matrix. Okay, now their formula for it, it's nothing but A is equal to 1 by 2 A plus A transpose plus 1 by 2 A minus A transpose. Now this is nothing but it becomes a symmetric matrix. Okay, if you have any of the matrix, you want to find the symmetric and skew symmetric matrix from it, then we can just use this particular formula. This is a symmetric matrix, this is a skew symmetric matrix. Okay, now coming to the next one regarding the skew symmetric matrix. Okay, if A is a skew symmetric matrix, then A power n is nothing but when n is an even number, then it becomes a symmetric matrix, and it becomes a skew symmetric matrix when n is an odd number. These are the basic important things of a symmetric and skew symmetric matrix. Coming to the few more important points of symmetric and skew symmetric matrix. The first one is every odd order skew symmetric matrix is in a singular matrix. What is a singular matrix? Is nothing but when the determinant of a matrix A is equal to 0, then it is known as a singular matrix. In the case of odd order skew symmetric matrix is nothing but like 3 cross 3 or 5 cross 5 matrix. Okay, we'll be getting in a singular matrix. Okay, come to the second one. Every even order skew symmetric matrix is a non-singular matrix. What is a non-singular matrix? Is nothing but when the determinant of a matrix A is not equal to 0. In the case of even order skew symmetric matrix, right? So like we'll be getting like 2 cross 2 matrix or 4 cross 4 matrix, so on. Okay, next one. Every symmetric matrix is an orthogonal matrix. Okay, what is an orthogonal matrix? Is nothing but when A into A transpose is equal to I, then is known as an orthogonal matrix. What is a symmetric matrix? Is nothing but A is equal to A transpose. Okay, it also satisfies that A is equal to A inverse also. In the case of a symmetric and orthogonal matrix, A is equal to nothing but A inverse also. Okay, coming to the fourth one. Every symmetric matrix is nothing but a non-singular matrix. Yes or no? It is nothing but determinant of a matrix A is not equal to 0 in the case of a symmetric matrix. Coming to the next one. Number of distinct elements in a n order symmetric matrix is equal to n into n plus 1 by 2. If you consider an example for it, the matrix A is equal to something like 1, 2, 2, 4. It is in a symmetric matrix. So number of different type of elements in it is equal to nothing but it becomes 2 into 2 plus 1 by 2, which is equal to nothing but 3. Yes or no? So check it. 1, 2, 3. There are 3 different elements or distinct elements in a case of a symmetric matrix. If you consider the order of a matrix is equal to nothing but 14, then number of distinct elements in it is given as 14 into 14 plus 1 by 2, which is equal to nothing but it becomes 7 into 15. Okay, which is equal to nothing but it becomes 105. Okay, this is nothing but a way to find the distinct elements in a case of a symmetric matrix. Similarly, for a skew symmetric matrix, number of distinct elements in n order skew symmetric matrix is equal to n square minus n plus 1. If you consider example for it, it's nothing but when A is equal to a matrix 3 cross 3 matrix like 0, 1, minus 2, minus 1, 0, 3, 2, minus 3, and 0. It is nothing but a skew symmetric matrix. The number of distinct elements is nothing but it is a 3 cross 3 matrix. So we can find it with this formula. It is given as 3 square minus 3 plus 1, which is equal to 7. Just count it. 1, 2, 3, 4, 5, 6, and 7. Yes or no? Come to the next one. Idempotent matrix is nothing but A square is equal to A. Okay. Then involuntary matrix is equal to nothing but X square is equal to nothing but I. What is I? I is nothing but an identity matrix. Come to the next one. Nilpotent matrix is nothing but A power n is equal to 0, where n is known as nothing but an index. Okay. These are the basic important points of a symmetric and skew symmetric matrix. The question: which of the following is true for the matrix A is equal to A of ij n cross n matrix? Okay. The first one, for a symmetric matrix, A of ij is equal to agi. So consider matrix A as a symmetric matrix. Okay. Consider this one as nothing but 1, 2, 2, 4. Okay. Now, if you consider this one as an A11, this is nothing but A12. This A21 is nothing but A22. Right. Now, in this case, just check up. A of ij should be equal to A of ji. I is nothing but a row, j is in a column. So check it. A12 is equal to A21. This to satisfied. So this is a correct one. Come to the second one. For symmetric matrix, A of ij is equal to 0. For I is equal to j. You consider this one, A11 and A12, they are not zeros. So this does not satisfy. Come to the third one. In case of a skew symmetric matrix, consider matrix B as a skew symmetric matrix. Okay. Which is equal to nothing but 0, minus 2, 2, and a 0. This is nothing but a skew symmetric matrix. Right. Now in this case, just check up is A11 is an A12 is an A21 is an A2. Here they are saying in the third step, A of ij is equal to minus agi, right? Row and column, okay? If they are interchanged, they should be in a negative sign, right? So check these two. It satisfies. So answer is correct. Come to the fourth one. For a skew symmetric matrix, A of ij is equal to 0, I is equal to j. I is equal to j, right? 1, 1 and 2, 2, right? A11 and A22. They are zeros. So this one also gets satisfied. So answer is nothing but 1, 3, and 4. Option B. Now come to the next question. The question is A symmetric matrix which is neither symmetric nor skew symmetric. A power T is an A transpose. The sum and difference of these matrices are defined as S is equal to A plus A transpose and D is equal to A minus A transpose, respectively. Which of the following statement is true? They're saying both S and D are symmetric, S and D are skew symmetric, S is skew symmetric and D is symmetric, and S is symmetric and D is skew symmetric. The basic thing that we know is nothing but the matrix A is there. It can be expressed in terms of a symmetric and skew symmetric, right? 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose, right? This is nothing but a symmetric matrix, right? Now this one is nothing but a skew symmetric matrix, right? If any square matrix which is neither symmetric nor skew symmetric can be expressed in this particular terms. So this one is nothing but, you can say this is not money in the question S, and this is nothing but a D. Then it has been satisfied in the option D. The next question. Question is given an A as an orthogonal matrix, A into A transpose whole inverse S, and they're given the A matrix. Okay. What is meant by an orthogonal matrix is nothing but A into A transpose is equal to I. I is nothing but an identity matrix, right? Here it is a 4 cross 4 matrix, right? So I would be also a 4 cross 4 matrix, right? Now in this case we have to find the value of A into A transpose whole inverse, then which is equal to nothing but identity matrix whole inverse. As we know that I inverse is equal to nothing but I only. That's only. So identity matrix of a 4 cross 4 matrix. We can write this one as nothing but matrix identity matrix 4 cross 4 matrix is nothing but, if you write it down, you get that's nothing but 1 0 0 0 0 1 0 and 0 0 1 0 and 0 0 0 1. This is nothing but an identity matrix of a 4 cross 4, right? So answer is option A.